Thanks for the invitation to the talk. So my name is Quan Wang. I'm from Google. Today I'm going to talk about speaker diarization at Google, especially how our systems evolved from modularized systems to large language models. Okay, so this is today's agenda. First, I'm going to give an introduction about diarization at Google. Then I'm going to talk about the different 4 generations of technologies we developed at Google, each leveraging different milestones of machine learning technologies. And finally, I'm going to talk about diarization with multimodal large language models, which is something we are currently working on, and we believe is the future of diarization. So let's get started with the introduction. A quick introduction about myself. I'm a senior staff software engineer at Google. I lead the hot word modeling team and the speaker, voice, and language team at Google. I'm also IEEE senior member, and I was a former machine learning scientist at Amazon Alexa team, which is also in Cambridge across the street. About our team, we are part of the bigger speech team at Google, which is around 300 people. The models our team built and shipped to production at Google include the OK Google, Hey Google hot word detection model, the speaker recognition and the voice filter model, then the language recognition and the speaker diarization models. For example, for speaker diarization, in Google Cloud, we have this Cloud speech-to-text API. It will take audio as input and output a text transcript. In this API, we have a configuration called the diarization config. If you enable the diarization in this config, you are able to set the minimum number of speakers and maximum number of speakers in the API. And the output response of the Cloud API will give you the transcript with each word allocated by speakers. We also have the on-device diarization solution. In the speech team, many of our models are ported to on-device, and the speaker diarization is one of them. If you have a Pixel phone, you should have the Recorder app. In the Recorder app, we launched this speaker label functionality. It's a fully on-device, a very small footprint, real-time streaming speaker diarization solution you can use to diarize hours long of meeting recordings without draining your battery. Apart from the products, we also tried our best to open source some of our code and algorithms. It's hard because some of our code have heavy dependencies on Google's internal infrastructure. We tried to extract some of them to be isolated from the Google ecosystem. And try to share them with the community. For example, the spectral clustering we used, and the UIS-RN, and also diarization LM, which we'll cover later. So the next part, I want to talk about our first generation of speaker diarization technology at Google, the modularized speaker diarization. So just in case some of today's audience are not very familiar with the concept and the problem of speaker diarization, if you search Wikipedia what is speaker diarization, you'll find this very standard definition. It is the process of partitioning an input audio stream into homogeneous segments according to the speaker identity. And to simplify it, it answers the question, who spoke when? If you look at this example, you have a streaming audio signal. It consists of 5 segments. The speaker diarization problem is to identify the segments of each speaker and find that the first, the third, the fifth segments are from the speaker 1, and the other two segments are from speaker 2. So that's the problem speaker diarization wants to solve. The very standard, very conventional, very classical approach of doing speaker diarization is through a modularized framework. The very common setup has these components: the feature extraction, voice activity detection, segmentation, speaker embedding extraction, and unsupervised clustering. Some systems have optional resegmentation, but that's not super common. So Google's first generation system follows this very standard setup. We first extract log-mile filter bank energies from the audio signal. We use the CLDN-based voice activity detector to detect the speech segments versus the non-speech segments. We use the hierarchical fixed length segmentation algorithm. And then we use an LSTM-based deep neural network to extract the D vectors, which is the name for the speaker embeddings at Google. and we finally use a refined spectral clustering to cluster these D vectors and use the cluster labels as the speaker labels. The good thing about the spectral clustering is that in spectral clustering, you can compute Laplacian matrix, and then you can compute the eigenvalues from the Laplacian matrix. Then you can use the maximum eigengap to automatically identify the number of speakers from the entire audio session, which is a very powerful algorithm. And we also find that it's very helpful if we apply some refinement operations on the affinity matrix before we compute the Laplacian matrix. This is kind of inspired by computer vision because the affinity matrix is just a matrix which you can treat it as an image, and you can just do standard image transform on it. For example, if you can apply Gaussian blur on the affinity matrix, it's kind of a data smoothing step. You can also do row-wise soft thresholding on the affinity matrix. This is very useful because it will sparsify and binarize the graph. We know that spectral clustering is basically a graph cut algorithm. If we can sparsify and binarize the graph, it will hugely improve the performance. So that's our first generation of speaker diarization at Google, a very standard modularized framework, nothing fancy. You can find lots of similar work from other teams, other companies. So our second generation is based on fully supervised diarization. If you look at the standard modularized pipeline of speaker diarization, we try to ask ourselves this question: what is the bottleneck in this system? And we found that there are many components in this pipeline, but there's one particular module that we cannot improve, even if you have lots of training data. That is the unsupervised clustering. So why unsupervised clustering is not good enough? So if we can just look at this very simple example, this is an image of two-dimensional data points. If I ask you how many clusters are there in this image, you can come with different answers. Like this is a butterfly shape, but the two wings of the butterfly are collected in the middle. So you can say there's only one cluster, but you can also say there are two clusters. There's simply no standard answer to this question because it's ambiguous. So that's the problem of unsupervised clustering. However, with the same input example, if I give you another example, I tell you that in the image on the right-hand side, I know for sure that there are two clusters. Then how will that influence your decision on the original napped example? Because there's already another butterfly shape that we know that has two clusters. So we can easily tell that the first original one should also have two clusters. However, with the same example on the left-hand side, if I give you another example telling you that this is another butterfly shape, I know for sure there's only one cluster in this shape, how would that influence your decision on the original example? We can see that because the other butterfly shape has only one cluster, so the first butterfly shape should only have one cluster as well. So now based on two different training examples, the same original input, we come up with different decisions, and that's something clustering cannot do for you. Apart from training examples, even if we don't have any training example, but if we know the order of appearance in the data points, it will also give us different decisions on the clustering result. For example, in this animation, in the left one, the points appeared in the left wing first, then appeared in the right wing. In the second image, they appeared alternatively in an interleaving way that is left-right. So that will also give us different decisions. If they appeared in the left first and then appeared in the right-hand side, it's very likely they are two different clusters. But if they are appearing alternatively in order, it's more likely it's just a single one cluster. So what are we learning from the above examples? So first, we know that unsupervised clustering algorithms are usually based on heuristics and rules. Even with lots of data, we can't improve the clustering algorithm. And also, most unsupervised clustering algorithms are order agnostic. For example, you run k-means, even if you permute the order of the data points, k-means still give you the same answer. So that are the two problems of unsupervised clustering. But with supervised clustering, we can do it differently. We can learn from training data, and we can leverage temporal information if we have networks like RNN or transformers. So there are many ways to do speaker diarization with supervised approaches, like EEND, TSVAD, and DNC. At Google, our first solution we propose is UISRN, which is short for Unbounded Interleaved State Recurrent Neural Network. So let's try to define the problem here. Assume that after the speaker embedding extraction, you have a sequence of speaker embeddings. We call that the observation sequence, which is uppercase X. For each embedding, you have the ground truth speaker label, that is Y. So the sequence Y, label sequence Y has the same length as the observation sequence. So now we want to build a model such that it can be trained with the pairs of X, Y from the training set. And now once the model is trained, given any new and unseen X, the model should be able to predict the Y sequence, and that is the inference. So UISRN is a probabilistic model. We want to model the joint probability between the pair of X and Y. And we break it down into 3 components. The speaker change part, the speaker assignment part, and the sequence generation part. So let's talk about the 3 different parts one by one. The first one is the speaker change. In general, you can use the generic form, but for simplicity, in the experiment we did, we just assume the speaker change Z follows a distribution that's like a coin flipping and with a constant parameter P0. The second one is more interesting, speaker assignment. So for this problem, we want to model when a speaker change happens. Is this an unseen new speaker, or is a previously seen speaker? And we model it as a distance-dependent Chinese restaurant process, or DDCRP. Just imagine that you go to a Chinese restaurant or any restaurant. You are part of a party. When you come to the restaurant, you can join a table. You may join a new table if your party hasn't arrived yet. You may also join a table with some people around it. And if there's a table with more people around it, you are more likely to join that table because that just indicates the party is big, and you are more likely to be part of that big party. So that is very similar to the problem setup of speaker diarization. If we have a speaker that is a very active speaker that spoke a lot in the past, it's more likely that this speaker will speak again. So that's our intuition to formulate the speaker assignment problem. The last part is called sequence generation. So here, we use a recurrent neural network. But what's special here is that we only have one set of parameters of the recurrent neural network. But we have multiple instances of the recurrent neural network. That means when we model different speakers, each speaker is a recurrent neural network instance. That means each speaker has its own states of the RNN. However, all the speakers, their RNNs share the same set of parameters. So if you look at this example, there are already 3 speakers who spoke in the past. Now, when we see a new embedding, this new embedding may be generated by any of the previous RNN instances for the past speakers. It may also initiate a new RNN instance. That means the new embedding is coming from a new speaker that's none of the previous seen speakers. So we find that UISRN is much better than unsupervised clustering algorithms like k-means or spectral clustering. Even if the UISRN inference is an online streaming inference, and k-means and spectral are both offline, and the performance comes from in-domain training data that hugely improve the performance. We also find that if we increase the amount of in-domain training data, the UISRN performance can be further improved. So we really achieved our goal that the more data we have, the better performance we have. We also noticed that as part of the end-to-end system, UISRN is a supervised component, but the end-to-end performance is dependent on many other components as well. For example, if we improve the quality of the D vector, it will hugely improve the performance as well, even if you always use the UISRN, because the D vector is the input sequence to the UISRN model. So finally, we find that if now we can replace the clustering module by UISRN, And now the entire speaker diarization system end-to-end becomes fully supervised, and which is good, means we can always train with more data and get better performance. However, is that really the true story? That once you have a system fully supervised, you can just collect infinite amount of data and get like perfect performance? Unfortunately, that's not the case. I will explain why. Because if you look at the data collection problem for speaker diarization, what's the diarization data looking like? If you worked with standard data sets like Fisher or Cohom, you should be very familiar with this format. So in the diarization data set, the audio part is conversational audio like telephone call. The annotation, we call that the time allocated speaker labels. For example, each row is like this, like start, that is the starting time of the segment, end, that's the ending time of the segment, and the speaker, that's the speaker allocation of the segment. We try to allocate some of the training data ourselves. We find that this is extremely expensive and error-prone because when we allocate the data, we have to frequently go back and forth to compare whether this current speaker is a previous speaker that we've seen before. And it takes lots of efforts to identify the accurate timestamp between the speech signals. And we found that doing a single pass of allocation of 10 minutes of audio, it will take a person about 2 hours. That's just too expensive and not acceptable for larger scale data collection. So we try to find other ways to allocate speaker diarization data to make it faster and easier. The first way we try is that we change the problem from who spoke when to who spoke what. This is because in most applications of speaker diarization, we don't really care that much about when. The accurate timestamp is not very useful. We just need to know who spoke what. And that's, in most cases, sufficient. For example, in meeting caption summarization, you don't really care about like, whether this speaker is speaking very fast or very slow. You just need to know which sentence is from which person. So the what means the text transcript from ASR here. So let's look at this example. So the left-hand side, this is the who spoke when annotation, and this is the who spoke what annotation. So from the left to the right, you no longer have to eyeball the waveform shape, the contours to identify the exact timestamps. You just need to attribute the speaker labels to each recognized word. That is much simpler and faster. So with this kind of who spoke what annotation, we can leverage sequence transducers to model the speaker diarization problem. Example transducers are like RNN transducer and transformer transducer. They have become the mainstream end-to-end framework for speech recognition, so it allows us to introduce new task-specific tokens to the output vocabulary we can use to model the speakers. In a standard framework, it should have encoder, decoder, which is also known as prediction network, and finally, a join network. The join network will output the sequence of output tokens. So our first application is medical speaker diarization. So in this work, we introduced two special tokens, a doctor token and a patient token. We just insert them into the output text sequence and model the speaker diarization problem as a sub-problem of the ASR problem. If you look at the example output here, hello, Dr. Jekyll, followed by a patient speaker. This means this sentence, hello, Dr. Jekyll, is spoken by the patient and followed by another sentence spoken by the doctor. So now speaker diarization becomes a pretty standard ASR problem. However, this work is just a row classification. The rows are predefined, and we know the maximum number of speakers is 2. So this can solve the in-domain problem of medical diarization, but it's not a generic solution for speaker diarization, because we know real speaker diarization should be permutation invariant. And we later introduced word-level end-to-end neuron diarization, or WEND. So this is trying to solve a slightly different problem. We are not trying to build a diarization model here. Instead, we say that we are trying to add diarization capability to any existing and off-the-shelf ASR model. This is a huge difference. That means we want to add new capability to an existing model, which we cannot touch. We have to freeze it in order to not change its already good performance on word error rate. So to do this, we have to freeze the encoder, decoder, and joint network of the ASR model. We introduced the two auxiliary networks to the framework, the aux encoder and the aux joint network. And we only train these two networks on the diarization dataset, and we keep all the ASR components totally frozen. And this diarization aux joint network, it will output a sequence of speaker tokens. And the speaker tokens are very generic tokens. It's no longer like a patient versus doctor. It's just a speaker 1, speaker 2, speaker 3. So we are not limited by the number of speakers, and we are not limited by the permutation invariant problem. So by doing this, we have to introduce another trick that is called sharing the blank logits from ASR. That means every time ASR joint network outputs a blank logit, we should also force the diarization network to output a blank logit. That makes the diarization at ASR outputs totally synced. Every time we have a new ASR word, we have one and exactly only one speaker label for that word. Okay, and by doing this, we achieved our goal that we added the speaker diarization capability to an existing ASR model without changing that ASR model. That means we have 0 word error rate regression. Okay, so that's how we never reached this who spoke what type of annotations. But we find that annotating who spoke what is still quite expensive. So we are thinking about how to make our annotations even faster, even easier, and even cheaper. And we find that the best way is to only annotate speaker terms instead of annotating speaker labels. So if you look at these two examples, the left-hand side is speaker label annotation is speaker A, speaker B, speaker A. But on the right-hand side, we only annotate the speaker term, means the speaker has changed from this one to this one. The best thing is that we no longer know that the third sentence is the same speaker from the first sentence. But the good thing is that you don't need to worry about that during annotation. While annotation, you no longer need to go back and forth to check a previous speaker. You are always focusing on the very near-term context and without having to look back. And that makes annotation very, very fast. And that's only just a minimal increment efforts on top of existing regular ASR annotation. When you have an ASR annotation project, you just add an appendix to the annotation instruction saying, oh, please also include speaker terms, without starting a completely new project saying you have to annotate the speakers. So that's the minimal cost annotation for speaker diarization. So with this kind of annotation, we can collect huge scale of speaker turn annotated data, much, much larger than speaker label annotations. And with this kind of data, what can we do? So we introduced this algorithm called turn to diarize. So in this framework, we only introduce one single additional token into the ASR output vocabulary. That's the speaker turn token. And we just model the joint ASR and the speaker turn prediction problem as a single standard ASR pipeline. And with the speaker turn, the rest of the diarization pipeline is pretty similar to the standard conventional approach. The only difference is that now we extract speaker embedding for each speaker turn instead of from each fixed length segment. And there are multiple benefits of doing that. First, we are going to have much, much longer segments. And we know that the longer the segment is, the higher quality the D vector or the speaker embedding is. So we guaranteed better quality of the speaker embeddings. And second, we are going to have much fewer speaker embeddings than before. That means we have less data points into the clustering algorithm. That means the clustering algorithm will be much, much more efficient. This is very important if you want to run speaker diarization on a meeting recording that can be multiple hours long. Like, for example, I want to diarize the entire SANE workshop recording. If we use speaker turn, we'll find that I train as the speaker who took 1 hour of audio. That is just the one speaker embedding. We don't have to break it down into like thousands of embeddings. Okay. Another benefit of using speaker turn is that each speaker turn is very very clean. The speaker embedding is guaranteed to be extracted from the same speaker. We don't have a segment that has like different speakers overlapped. And with speaker term, we can also apply additional constraints to the spectral clustering algorithm. And also, we have a very small engineering trick on top of the turn-to-diarize algorithm to make it run efficiently on the device. That's called the multi-stage clustering. The idea is very simple. When you ship a diarization product to the user can use it in whatever they want. They can just diarize 2 seconds of audio. They can diarize 1 minute of audio. They can also diarize 10 hours of audio. So we have to use different clustering algorithms for different lengths. For example, if the input audio is very short, like just 2 seconds, there are not sufficient data points for you to run k-means or clustering. So we have to use a predefined threshold and just do standard hierarchical clustering. If the audio is several minutes long, that means you have sufficient number of speaker embeddings. And in that setup, spectral clustering will give you the best result. And if the audio is like 10 hours long, that means you have to really worry about the system health and the battery life. So in that case, we have to enforce an upper bound of the computational cost and the memory of the algorithm. So we introduced a pre-clustering algorithm to enforce this upper bound. OK, so far, you may find some contradiction in my presentation. Like first, I said that we want supervised algorithms so that we can leverage in-domain training data. And later, I said that we have to reduce the cost and improve the efficiency of data collection. And we went back to speaker turn annotation, and we still leverage unsupervised clustering algorithm. So this is unfortunately true because the reality of the data. However, fortunately, we have LLM right now. And the good thing about LLM is that it can be fine-tuned with a very small amount of data, and that gives us some other directions. So next, I will talk about diarization LLM. How many minutes do I have right now?
You've got a countdown right here.
Oh, OK, I have 40 minutes. OK, that's fine. So the first question we ask ourselves is like, what can LLM do for speaker diarization? So the right-hand side is I was just typing conversations to the web UI of a commercial LLM. And we find that you can do pretty fancy stuff for us. In summary, we find that it can correct speaker diarization errors. In the demo, it can also autofill speaker names, autofill speaker roles. And not in the demo, but we also found that it can perform ASR and diarization orchestration. And today's focus, we will focus on how LLM can correct speaker diarization errors. So what kind of errors we are talking about here? So if we look at the speaker diarization errors, it can come from any component of the pipeline system. For example, ASR has errors, diarization has errors, speaker embedding has errors. But there's one particular type of error that can be very easily fixed by LLM. That's the few words of errors from the orchestration module. So what's the orchestration module? In most standard commercial diarization solutions, the ASR system and the diarization system, they are from separate pipelines. They are trained, developed, and fine-tuned with different training data, and they use different algorithms. So that means their timing information can be very misaligned. And when we combine the results of the two systems using the timing information, we get lots of like few words of errors from this behavior. Okay, so diarization LLM is the high-level framework such that it takes the existing ASR and the speaker diarization system output, which we call the reference, which has the ground truth as reference. And diarization LLM tries to take hypothesis as input and will generate the reference. And here is the diagram. You can see that ASR and speaker diarization, these are frozen. We don't touch them. They produce outputs which are orchestrated. Then we take the orchestrated result as the input. We have a prompt builder, a trainable LLM, a completion parser, and it will generate something that's more similar to the reference. So this seems to be an easy problem, but there are several challenges. The first challenge is that we know that LLM takes text as input, and it will generate text as output. So the first problem is that we need to reprint everything as pure text. So this is a pretty easy problem. For example, if we have a word sequence from ASR, we have a speaker sequence from speaker diarization. They have the same sequence length. For example, the 1 and 1 means good morning from speaker 1, 2 to 2. That means how are you from speaker 2. So we merge them into this single pure text representation. And we only insert a speaker token when the speaker has changed. So this is very readable, and now everything is text. Both the hypothesis and the reference are just the pure text. Another challenge is that we know that if you have played with any LLM API, you know that LLMs have this max sequence length input. This can be like thousands of tokens, but we find that in diarization datasets like Fisher, one conversation may have more than 50,000 words that easily won't fit the length limit. So our solution is that we recursively segment the word and speaker sequences in the middle until we fit the length limit. So now we have both reference and hypothesis in pure text format, and they fit the length limit of the LLM. Does that mean that we can just throw them into the LLM trainer and get what we want? Unfortunately, that will not just work, because now if you look at the reference and the hypothesis sequences, they have both different words and different speakers. Different words, that's because, of course, the ASR system is not perfect, so you cannot expect the ASR words are the same with the reference words. So the problem is here, if you try to throw them just into the LLM, is that you are asking the LLM to solve two problems at the same time. You want the LLM to correct ASR, and you want LLM to correct diarization. This will cause a lot of confusions to the LLM. And if you use a medium-sized or small-sized LLM, and you don't have that many data, this just won't work. So we have to simplify the problem for LLM. The way we do is that we guarantee the words are always the same, and only the speakers are different. This will enforce the LLM to only focus on correcting diarization errors and ignoring any errors from ASR. And to do that, we introduced an algorithm called transcript preserving speaker transfer, or TPST. So what is TPST? Don't be scared by the name. It's a pretty simple algorithm. We assume that we have two sequence of diarized transcript, and TPST will transfer the speaker labels from the source to the target, such that the transferred speaker labels are associated with the target words, but it's more consistent with the source speakers. I know it's still not straightforward, so let's look at this example. So we have a source sequences, the source words, source speakers. Each source speaker is for one source word. And we have the target words and target speakers. And after I do the transfer from the source to the target, I get this sequence called the transferred speakers. It has a one-to-one correspondence to the target word. So you see that the sequence length is the same as target. But if you look at the pattern, it's more similar to the source speakers rather than target speakers. So with this TPST algorithm, we can build our prompt and completion pairs for the LLM training. And there are three flavors to do this. The first flavor is called hypothesis to oracle. That means the words are always from the hypothesis, both in the prompt and completion. The prompt is just simply the hypothesis. But for the completion, we have to transfer the speakers from the reference. And the second flavor is degraded to reference. So this is just the completely opposite of the first one. All the words are coming from the reference. The completion is just the reference itself. But for the prompt speakers, we have to transfer the hypothesis speakers to the reference words. And with these two kinds of prompt completion pairs, we guarantee that when we train the LLM, the input and output always have exactly the same words. You can see that here, input, output, both hypothesis words. Here, input and output, both reference words. Only the speakers are different. And the length of the speaker sequences in input and output are exactly the same. So that will make LLM training much easier. And of course, the last type is just the mixed flavor, which is a mixture of the first two. So to do the diarization LLM experiments, we use the feature training set. We evaluate on feature and cohom. We can't use diarization error rate because that's for timing information. Now we don't have timing information, so we have to use WDER and CPWER. For the models, ASR, we just use USM. Diarization is to diarize. LLM, we tried PALM, NAMA 2, NAMA 3. And for prompting, we tried 0 shot, 1 shot, and fine-tune the LLM. So first, how do we do 0 shot and 1 shot? 0 shot is just describing the task for diarization correction. It's just a simple description. 1 shot is just like including a very simple example of how we expect the format to be. And here are the results. So if you look at the 0 shot and the 1 shot, unfortunately, they don't work at all. They will be much, much worse than the baseline. So we learned, so it's surprising because like previously I showed you a very simple demo where 0 shot just works. But unfortunately, building a demo that works is pretty easy. But if you want to demonstrate with a real evaluation data set, 99% of the cases, it won't work at all. Later, we tried the fine-tuned version of the LLM, and it works surprisingly well. For the best model we see, we have around 50% improvement of the word diarization error rate, which is not just improvement we've seen in the past few years. So this is quite exciting. We also keep asking ourselves, like, what kind of errors are corrected by LLM? So we find 3 different patterns. There are more patterns, but these 3 are most common. For example, a sentence is being broken in the input. LLM can easily put them together. For example, this one is it's more of from different speakers. But if we just look at the text, we know this must be from the same speaker. LLM corrected that. The second type is disfluency. Like someone is saying, yeah, I live in Houston. LLM recognized this is disfluency and fixed that. Another pattern is someone was speaking, someone else interrupted you, and LLM can easily fix that as well. For example, here, this is, I wouldn't either unless. So we know that this must be from someone else. So LLM fix it easily and assign to speaker 2 and put the text before and after to speaker 1, which is great. Okay, so we are excited about diarization LLM, not just because we are seeing a huge improvement. It also has huge potential for production because it works with any off-the-shelf ASR and diarization systems. We don't have to change anything in the existing ASR model or existing diarization model. We just fine-tune diarization LLM as a post-processing and plug it into the existing production system, and that will just work. Okay, we have released this diarization LLM Python library, so if you're interested in it, you can try it. You just install it with pip install command. We have this core algorithm, the transcript preserving speaker transfer, so you don't have to implement it yourself. We share the scripts for training inference with Anthos and Nama, which are both open source framework. And finally, we also offer the function for you to compute the metrics we use, the word error rate, word diarization error rate, and the CPWER. So why not just look at the real demo? This is a demo built with Nama 3 on TPU, sorry, on CPU. So in the left, you can just type your prompt. I don't want to type anything, so I will just use the predefined prompt. Why not use this one? This is speaker 1. This demo looks really, the good should be from speaker 1, but now I assume there's a mistake. It's from speaker 2. Thanks, I'm glad to hear that. This should be from speaker 2. Let's hit the submit. Let's wait, because it's CPU, so it's quite slow. If it's GPU or TPU, it should be very fast, but I don't want to pay for it. Okay, you can see the output is being streamed. Speaker 1, this demo looks really good. Okay, it's been fixed. And speaker 2, thanks. I am glad to hear that. And end of document, that means it's done. Cool, that's a demo. Okay, let me. Okay, so the conclusion so far, our best current on-device streaming speaker diarization is conformal ASR tended-diarized with multi-stage clustering. Our best offline is USM tended-diarized and diarization LLM. We are not only driven by technical advances in machine learning and speech. We are also largely driven by the constraints and the realities of data and the computation resources. And next, I want to talk about diarization with multimodal LLM. So we have different generations, like generation 1, 2, 3, 4, each inspired by different machine learning technologies, like deep learning, supervised clustering, sequence transducers, and LLM. So we ask ourselves, what's the next foundational technology that should change our way to do diarization? We believe that's multimodal LLM. So there are lots of works emerging in the community. I don't want to mention all of them, but we asked ourselves the question, like, can we just do diarization by prompting? We have a prompt of diarization task. We have an audio. We just expect the LLM to give us output. Will this work? So we designed this zero-shot prompt, starting by the task description, followed by the format description, followed by an example format, followed by some text to discourage hallucination and unwanted text. So we came up with this magic prompt and throw it into Google AI Studio, and let's see how it works. This is the audio file.
They can create creativity, and we've seen that in various places in Europe when creativity created from being multicultural society.
What do you think of that, Luke?
Maybe I should just say that here is the magic prompt we come up with, and we ask Google AI Studio to listen to the audio and complete the task. And here is the output we saw. Now you can compare the audio and the output. You can see that is
Block made some other very controversial comments, including that it's linked to human genetics, that means that ethnic groups can't get along. What do you think of that?
That went too far, clearly. But
okay, I will just stop here. The message is that the zero-shot magic prompt just worked out of the box without fine-tuning the model at all, even if the model was not trained to do so. And but the lesson we learned from diarization LLM is that when you have a cool demo, which means you probably handcrafted the input, and it may not work with any eval set at all. And we try to throw this magic prompt into a testing pipeline for feature testing set to see what we get. And it's true again, like it's much, much worse than any baseline we have. Compared with the diarization LLM baseline is more than 10 times worse. So zero-shot LLM, you can show a cool demo post on LinkedIn, but if you test on anything real, it just doesn't work. So that's very unfortunate. So that means there are still many questions to be answered. So those questions include, will few-shot prompting work if zero-shot prompting doesn't work? And how can we fine-tune the MLLM on diarization tasks? If we fine-tune MLLM, like how are we going to handle the model input length limit of the model? What if your audio is too long to fit into that input? And how do we carry speaker states across different training batches and inference chunks? At Google, we are actively addressing all of these challenges. But we all agree that diarization is a new hot topic in the era of LLM. Yeah, that's the end of my presentation. We should have time for questions.
All right. I'm going to use this one. You can keep this one. Are there questions from the audience? I think we have a couple of mics in the back that we need. You can, use this one.
Check, test.
Yeah, go ahead.
Okay, this is my part of the diarization, so you can start logging me now. So is the MLLM using the latest diarization techniques that you presented, or are they two different parts of Google?
Sorry, you mean this one?
Well, the one that got the WDER score. So you just presented all these new diarization with semi-supervised and supervised techniques, but are those?
This is the zero-shot. So it's
I see,
it's
zero-shot.
Like a for loop running this one.
Okay.
On feature.
So your next task is to plug in your diarization techniques into the MLLM?
I cannot disclose that, but hopefully we can disclose it very soon. Yeah.
Second question, is there a annual diarization stress test challenge that everyone can compete in? Like there's, the chime, the speech and noise recognition challenge.
Yeah,
Are there any open challenges of which you're aware?
I am aware. Chime has a channel. Chime has a track for diarization, if I remember correctly.
Oh, cool.
And there's also something called diehard. We never attended from Google, but I know it has a leaderboard, and people are pretty excited about the new results from the diehard. And I read lots of papers from diehard challenge as well.
Cool. Thanks.
Thank you.
Thank you for the talk. You said that manual labeling of diarization data sets is very hard, and so you've coupled with speech recognition systems and trained them jointly.
Yeah.
Have you explored an alternative path where you just manually, synthetically create those diarization training data sets, either speech synthesizers or something?
That's a very good question, and we did try something like that. So I think not just I saw lots of existing work from academia and other companies. They just use existing single utterance data sets and concatenating them to create synthetic speaker turns. The unfortunate thing is that the concatenation sounds completely different from a natural speaker turn. Even human can tell that. And if you train a model on that, if the model will easily overfit to the concatenated utterances. So that simple approach won't work. But I'm aware of that. I saw some recent papers on multi-talker TTS. They just, the TTS model is trained and is trained with like natural speaker turns, and it will generate conversations with speaker turns. I never tried that, but I think that's very promising. We should probably try that soon.
Thank you.
I think we maybe if you can unplug your computer while Greta's setting up, maybe you can answer one last question.
Sure.
I think lots of people are here because people are interested in using the diarization results for their subsequent processing, for example, sentiment analysis or TTS. For these people, the timing boundaries of each speaker's utterance is important. Do you mean that later on we don't have to look at the DER, or do you have any thoughts on this? And the second question is, you haven't commented on overlapping.
Otherwise, I won't remember your first question. Okay. For the first question, I'm not saying time boundaries are not important. I'm just talking about for the specific applications that we are trying to launch our products to. In those applications, time boundaries are not critical for the user experience.
And how does the second question is, how does the overlapping of the speakers work in your system?
In most of our existing work, we don't assume there will be overlap speech, but diarization LLM and tend-to-diarize and the word level end-to-end diarization is an exception because we are expecting the ASR system to be able to separate overlapping speech, and the diarization is built on top of that. Okay. So the ASR system is trained with overlap speech, so that will just simply solve the problem. But if they overlap too much, it will still not work.
Thank you.
Yeah.
All right, let's thank Quan again.